A very good evening, good afternoon, and good morning to all. I, Dr. Pallavi Saxena, SSC member of iLEAPS, and Dr. Samina, Project Administrator, iLEAPS, welcomes you all on the occasion of our 10th talk in iLEAPS Global Colloquium Series 2022. So iLEAPS is an integrated land and atmosphere interactions, which is a global research project of future Earth. iLEAPS provides understanding of how interacting physical, chemical, and biological processes transport and transform energy and matter through the land-atmosphere interface. So the prime objective of this colloquium is to introduce the scientific community with the distinguished and significant work of eminent scientists all over the world. It's a very bright opportunity for early career researchers to interact with the speakers and establish the bridge between the ideas and knowledge through this platform. So our today's speaker is Dr. R. Subramanian, who is a senior scientist at Environment and Sustainability Center of the Qatar Environment and Energy Research Institute, TD, where he leads KIRI's research on sensors for air quality and climate. He is also a research fellow at the Kigali Collaborative Research Center, a visiting researcher at OSU CNRS, France, and an adjunct faculty member in the Department of Mechanical Engineering at Carnegie Mellon University, Pittsburgh, US. Over the past 2 decades, he has worked on chemical characterization and source apportionment of ambient organic aerosol, single particle measurements of black carbon and mixing state, cook stove and vehicle emissions, and methane emissions from natural gas facilities. Recent accomplishments include leading the development of the real-time affordable multi-pollutant monitor, co-leading the deployment of a 50 ramp network in and around Pittsburgh, and establishing the Afric Air Monitoring Network, a collaborative international effort using reference grade and lower cost monitors in many cities across sub-Saharan Africa. So today he will be speaking on applications of low-cost air quality sensors in different monitoring regimes worldwide, where he used to discuss that how low-cost sensors can implement in regular networks in well-monitored cities while filling in air quality data gaps in under-monitored cities. So now I would like to welcome Dr. Subramanian. Now, Dr. Subramanian, the floor is all yours.
Great. Thank you, Pallavi, for that introduction. And hopefully you can hear me okay right now.
Yes.
So thank you again for this opportunity to discuss my research that I've conducted over the past several years. As Pallavi mentioned, I'm a senior scientist at the Environment and Sustainability Center at the Qatar Environment and Energy Research Institute, which is part of the Hamad bin Khalifa University and the Qatar Foundation in Qatar. I also hold appointments at the Kigali Collaborative Research Center and at Carnegie Mellon University, where this research started. So let's first acknowledge my, sorry, oops, okay. All right, so I'm still trying to figure out how this GoToWebinar works, but hopefully now you can see the second screen. Essentially, acknowledge my collaborators, my manager, the Senior Research Director of ESC, Mohammed Ayub, and my colleagues, Rami Alfara and Jamjad Musakuti, who are working with me on the research in Qatar. In Pittsburgh, we have a number of collaborators, Albert Presto and Alan Robinson, and Naomi Zimmerman, Carl Mealings, and others. The names in blue are people who are either postdocs or graduate students at the time that they were working on this project. And so essentially the names in blue are early career researchers. And so there are also a lot of professors, especially in Africa, Kofi Omega, Alison Hughes, Rebecca Garland, Jimmy Gasore, Michael Guattari, and others who make up the AfriCAD network, who are helping me on the research in Africa, and I work with them very closely. The funding in the US, it was from the US EPA and the Heinz endowments. And for the work that was conducted at OSU-FLU and continues to today, was from the ANR Make Our Planet Great Again program, as well as from the NSF CAMPSNet program. As you may know, air pollution is responsible for several million premature mortalities, as estimated by the Global Burden of Disease and the Health Effects Institute. And one of the key pollutants is particulate matter, PM2.5 and PM10. There are also gaseous criteria pollutants like ozone, nitrogen dioxide, sulfur dioxide, and carbon monoxide. And these are regulated in many countries using their national standards with the WHO guidelines as aspirational goals oftentimes, because they're much more strict than all national standards. A key feature or requirement for managing air pollution and improving air quality is air quality monitoring. Now, traditionally, this is conducted with reference grade monitors. So here we see the reference grade monitoring station at Mito, Rwanda in Kigali. These are my colleagues, Jimmy Gasore, Theobald Habineza, who's now doing a PhD at Carnegie Mellon, and Professor Michael Guattari. And so this is a station here in Kigali, which is the only reference monitoring station in Rwanda. The instruments as shown here, they generally are, sorry, just this one here, okay. These reference monitors here for different gases and PM are generally $10,000 to $30,000. They require air-conditioned shelters, and they're also high accuracy, but also require a lot of maintenance. And so even in a city like Paris, there are only about 11 or 12 reference grade NO2 monitors. This is a map I got from OpenAQ, which is a wonderful resource for air quality data worldwide. And of course, many of these many countries in the global south even lack reference grade monitors or have very few reference grade monitors. And so the idea is, how can we use low cost sensors? That is the other alternative. These are typically small sensors. That's one sensor in the background. And these are typically anywhere from $250 to $10,000, but a factor of 10 to 20 cheaper than reference grade monitors. They're small footprint. They can be solar powered, but they can be affected by temperature and relative humidity, and they may not be quite specific to the pollutant of interest. So we need to actually correct for these interferences before we can use them. So one such low-cost monitor that I'll talk about a lot today is the Real-Time Affordable Multi-Pollutant Monitor, or RAMP, which was developed by my group at Carnegie Mellon in collaboration with Sensevere, a small company in Pittsburgh that is now owned by Sensit, and it's based in Indiana. Just to get this out of the way, I have no financial interest in the company, but we work closely in the development, and I'm probably one of their largest customers for the RAMP monitors. It uses electrochemical sensors for gases, carbon monoxide, ozone, NO2, and SO2. It uses optical nephelometers like a Met1 neighborhood PM monitor or a purple air monitor or a flat tower sensor for PM measurements. They come with GSM communication and an onboard SD card for local data storage. We have published a number of papers on this, with the first one led by Naomi Zimmerman, who was a postdoc at that time and is now a faculty member at the University of British Columbia, and Dr. Carl Malings, who was a postdoc as well, working with me, and is now a research fellow at NASA. And so the work that Dr. Naomi Zimmerman did, essentially we compared lab calibrations where we are exposing these sensors to different concentrations of calibration gas, well-known calibration gas at different temperature and relative humidity conditions. The other option is to collocate the low-cost sensors with our reference monitors in typical ambient conditions where we also want to use the sensors. And what you find is that the lab-based calibrations might be okay for something like carbon monoxide, but they field-based calibrations, especially using machine learning techniques like random forest uh, methods, are really required to get good data quality. So here, the green boxes are the lab-based calibrations. So this graph here shows the precision error as defined by the US EPA, and this is the bias error. And so the green boxes are with the lab-based calibrations. So you can see that for NO2, the lab-based calibration has a precision error of greater than 50%. Whereas with random forest, you can get that error to closer to 20% or 30%. For ozone, the ambient collocation-based precision error is less than 20%, and the bias is also less than 15%. That's in the magenta. And so with machine learning techniques and with ambient collocations, we can get pretty good data quality out of these low-cost sensors that can be used to supplement a regulatory grade monitoring network. Now, optical PM sensors, they essentially work on the basis of light scattering or nephelometry from particles. And when we compare, for example, the purple air PM2.5 monitor on the y-axis with your reference grade beta attenuation monitor from on the x-axis, we find about a factor of 2 difference between the values at times, especially biased at higher relative humidity. So here the markers are colored by relative humidity. So at higher humidity, you get a greater bias in the sensor measurements. And this is because primarily because light scattering increases the functional particle size, and at higher humidity, the aerosols are hygroscopic aerosols will grow, increasing the apparent particle size. Whereas reference grade monitors measure report data at a particular, like around 35% relative humidity at dry conditions. And so we need to apply these, correct for these known artifacts, as well as changes in size distribution between the factory calibration. For example, the purple air are based on plant hour sensors that are calibrated in Beijing and Shanghai from about 10 years ago, and which is very different from the aerosol size distribution and chemical composition in Pittsburgh. And so we need to correct for those differences. And so with Carl Mailings, we published this in Aerosol Science and Technology. We're able to reduce the mean absolute error from 4.2 microgram per meter cube to about 2.7 microgram per meter cube on an hourly average basis, reduce the bias from 2 microgram per meter cube to almost 0.46 microgram per meter cube, almost zero. And with the help of some averaging, so this for 1 hour data, for about 1 day or even 10 days of averages or annual averages, the uncertainty is reduced to below 10% of ambient PM2.5, which is getting close to reference monitoring status. And so how do we actually use these low-cost sensors in a city like Pittsburgh, which is fairly well monitored with regulatory grade monitors? So we want to acknowledge the progress that the US EPA has made over the years, along with the local air pollution agencies like the Allegheny County Health Department. So this was back in the day, about 50 years ago in Pittsburgh, where you could barely see the opposite building, and now the same view. We have made a lot of progress in cleaning up air pollution over time, but we are still at least a couple of years ago, Allegheny County, which is the home of Pittsburgh, was still in non-attainment for PM2.5, SO2, and ozone, which essentially the standards have been tightened over time. And we find that there's a lot of industrial activity and other commercial activity that's creating pollution in the green areas, which are environmental justice areas. And so how do we monitor air pollution there and make sure there aren't hyperlocal hotspots, for example, that can create higher exposure for people living or working in those areas? So what we did is, so here we deployed about a high density network of over 50 ramp monitors in Pittsburgh. So the squares show the locations of reference grade monitors operated by the Allegheny County Health Department. We complemented that with a 10 times denser sensor using the ramp network. We worked with community organizations like the Group Against Smog and Pollution and Clean Water Action. And we had a lot of volunteers requesting monitors at their houses or their schools. And so we have deployed this network, collected data since 2017, and the data are available on OpenAQ. And we also provide monthly reports to local communities to address questions that they may have. But scientifically, what new information does this high density network provide in a city like Pittsburgh? Uh, so uh, in Pittsburgh, generally speaking, the wind is either from the south or the southwest. So looking at the effect of wind direction and large point sources on pollution across Pittsburgh, what we find is that we can divide the data into concentrations when the wind was from the southwest or the west, which is on the x-axis here, or when the wind is from the south of Pittsburgh, that's on the y-axis here. And we find that when the wind is from the south, pollution increases in many places across Pittsburgh, sometimes as much as 70% higher. The red markers are the median of the measurements, and the light blue markers are the 85th percentile, so higher concentrations. And so some sites don't really see a significant impact of the shift in wind, but sometimes some sites are really affected by this. And when we look at where these sites are, so here this map here shows the locations of the different sensors, and the markers are colored by the difference in PM2.5 due to this wind change. And we find that the locations here to the east of Pittsburgh are, this is Pittsburgh generally speaking, and then the east side of Pittsburgh, you get a great impact of the shift in wind, whether the wind is from here or when the wind moves from here from the south. And so what happens, so there are the industrial facilities, this Clairton Coke ovens, this is the Braddock Steel plant. Pittsburgh was a steel town. There is still a lot of steel manufacturing in the area. But when the wind is from the south, as you can see by this arrow, we get more pollution directly hitting the east side of Pittsburgh. That is what is leading to higher pollution in Pittsburgh. And what is the impact of that, of those sources? We can, Rose Eilenberg, who was a graduate student at CMU, estimated that the long-term contribution is 0.3 microgram per meter cube out of an annual average PM2.5 of 10 microgram per meter cube in Pittsburgh. So it doesn't seem like a lot of effort, maybe 3%, but there are episodic contributions of up to 1.6 microgram per meter cube. That's average across the entire network, again, with some locations getting the brunt of it more than others. And so this is what is the power of a high density network, ability to map the impact of point sources on air quality across a region. And now coming to the present day, essentially, I now have moved to Doha in Qatar, and which is a really rapidly growing city in a desert environment. The population of Doha or Qatar has increased by about 50% over the last 10 years, related probably to the activities around the World Cup, which will start in 39 days from right now. Of course, being in the desert, we have a huge impact of dust storms. So you can see this model forecast by my colleague, Dr. Christos Fontoukas. And so he's running WRF-Chem and dust parameterizations, and you can see this dust storm essentially enveloping the whole region. And so this day we had PM10 greater than 5,000 microgram per meter cube, and his model is able to capture both the timing and the magnitude at the peak quite well. We are able to predict these things. And so when such sandstorms hit Doha, then obviously all of Doha is basically seeing 5,000 microgram per meter cube. But we also have a network of 6 reference grade monitors operated by Kiri. You can see here, Kiri, this is my office over here. Ash-Shahani is the regional background station that's more in the desert. Tumama is a football stadium, American School of Doha, Hamad Medical, and Al-Wakra, so different locations across Doha. And essentially the wind is often from the northwest going to the southeast. And so this is basically in line. So you'll see the progression of pollution across these places. But when we compare, for example, Wakra in the yellow-orange markers with Kiri, or Al-Tumama in the blue markers with Kiri, we see significant intra-urban variability in air pollution. And in particular at Tumama, there has been a lot of construction activity over the last couple of years, which has led to really high pollution at the stadium due to construction activity. But whereas Wakra, there is a micrometeorological effect with the sea breeze going on here. We still need to understand the dynamics properly of the interaction between the sea breeze and the marine environment and the climate over Wakra, but essentially that leads to periods of much cleaner air quality in Wakra than at the rest of Doha. So there are these, sort of uh, uh, multiple factors here that lead to hyperlocal air pollution across Doha when there isn't a huge sandstorm blanketing the city. And so that is why we are establishing the Doha Air Quality Sensor Network, or TAXNet. So we have over 50 low-cost sensor nodes. This is our Kiri reference monitoring station with a number of low-cost sensors co-located with the station for calibration. Uh, so we have Colloquium modular PM nodes, we have sensor ramps, we have clarity nodes, and in addition to our Kiri station, which is sort of a urban background station, we are also locating it at roadside locations and regional background locations. We have made a lot of progress in actually processing the data online, and we are now able to apply our correction models so that we get real-time data from the sensors in near real time. And so we need to look at how these PM sensors behave, and there has been a lot of work over the last few years characterizing these low-cost sensors. In particular, this work by Kula, published in Atmospheric Measurement Techniques. They sent in different sizes of aerosols into the sensors and compared with the reference monitors. And what they find is that the plant tower sensor, the PMS, which is very common and it's used in the purple air, even though the manufacturer says there are 3 different size bins and reports counts in each of the size bins, they're all seeing the same essential aerosol, and they're usually sensitive only to sub-micron aerosol. So these sensors cannot really be used for measuring particles bigger than 2 micrometers. And so you can also look at this, for example, here, this on the y-axis, the clarity node, which is very popular as a low-cost sensor. I believe the Breathe London network uses clarity nodes right now. And the x-axis is an OPC, also a lower cost monitor, though not so it's still a proper optical particle counter. And so for PM 2.5, they seem to be the salmon colored dots. They seem to be reporting the same value for PM 2.5, but for PM 10, which is in the cyan magenta markers, the clarity node significantly underestimates PM 10. And the underestimation is much worse when the coarse fraction of PM is dominant. That means that there is more dust in the atmosphere. So maybe the clarity nodes and such nephelometric PM sensors are okay for PM 2.5, not for PM 10. So there is still value in using these sensors. But when we compare the clarity nodes with our Kiri reference monitors, which are beta attenuation monitors, we see huge disparities between the reported values, sometimes much higher than the BAM, sometimes much lower than the BAM. And this is, we understand why the sensors report higher values in the BAM, and this can be attributed to hygroscopic growth, for example. The marker size here is an indication of the coarse fraction of PM10. So when the marker is small, it's mostly submicron aerosol, combustion aerosol, which is also where hygroscopic growth is a factor. And so it ends up reporting higher. We can correct for that, as we have seen before. But when the markers are larger, when there is more dust in the air, the clarity node reports much lower values than the BAM, and we can't really correct for that because these sensors are not sensitive to particles bigger than 1 or 2 micrometers. You cannot really report what you don't see, essentially. And so we have now moved on to the Colloquium modular PMs, which include an nephelometer and an OPC, an optical particle counter. So there are a number of Colloquium has done a very nice job assuming size-dependent density, hygroscopic growth corrections, and aspiration efficiency. So we have collocated these sensors with our air quality monitoring stations, which include a BAM for PM 2.5, but also a FIDAS for optical aerosol, which is an aerosol spectrometer that is TUV certified for PM 2.5 and PM 10. And so we are basically comparing an optical-based low-cost PM sensor, which has an nephelometer and an OPC, with a reference-grade optical aerosol spectrometer, which is reference certified for PM 2.5 and PM 10. First of all, the modular can give you both the nephelometric PM 2.5 as would be reported by a clarity node or a purple air monitor, and that's what we're comparing here on the y-axis, with the reference feed as PM 2.5 on the x-axis. And what you find is that the modular nephelometric PM can be a factor of 10 lower than the FIDAs. And this is likely to happen when, so here the cyan coloring on the markers indicates that the PM1 is a dominant fraction of PM2.5, whereas the magenta indicates that the supermicron aerosol, PM1 to PM2.5, is the dominant fraction of PM2.5. And so when basically coarse or supermicron aerosols are prominent, the modular nephelometric PM sensor cannot see that, and it significantly underreports, as you're seeing for the clarity nodes. So we look at the, uh, combined product, which is the OPC plus nephelometer, and now we see that there is some proportionality between the modular PM and the FIDAS PM 2.5. It's off by a factor of 2, not by a factor of 10. So there is some hope, but there is still discrepancy between the PM sensor, low-cost sensor, and the FIDAS. So what is the root of this? Now, since it's an aerosol size spectrometer, we can actually look at the comparison between PM1 from the modular and the PM1 from the FIDAS, the 1 to 2.5 micron aerosol from the modular and the FIDAS, and the 2.5 to 10 micron aerosol from the PM modular and the FIDAS. So the coarse aerosol are in the orange, so there is some lot of discrepancy here. I think the OPC still needs some work. But if you look at 1 to 2.5 micron here, so if you look at the lower end, which constitutes PM 2.5, so the orange, the green markers are the PM1 fraction, which is mostly from the nephelometer, and we find that the PM1 of the modular is about 40% higher than the FIDAS PM1, whereas the supermicron PM 2.5, which is 1 to 2.5 micron PM from the modular, is only about 30% of the FIDAS, but at least it's a very strongly correlated R-squared of 0.85. And so this suggests that there is something about aspiration efficiency that needs to be corrected into that data from the modular PM. So we can apply these very strong linear correlation corrections to the modular PM data. So we started with this value here, where it's the modular PM is much lower than the FIDAS, and we apply those corrections from the comparison, and we come up with R-squared of 0.82 and a slope of almost 1. And so this is acceptable for low-cost sensors. And the FIDAS is generally about $30,000. The modular PM is about $1,500. So by a factor of 20 cheaper, you can get reasonably comparable results, which is essentially the hyperlocal air pollution monitoring that you need to do without deploying a network of FIDAS instruments. And so we have applied this now again in Doha. We have a lot of reference grade monitors, but we also have large sporting events, for example. So we can deploy reference grade monitors everywhere. And so we are looking at deploying sensors at the stadiums of the World Cup. So this is the first, Qatar 2022 is the first football World Cup to actually implement air quality monitoring and management as part of their sustainability plan. And so we're using low-cost sensors and on-site observations to look at pollution, hyperlocal air pollution from stadium-related activities. So we have found that diesel generators are a prominent source of pollution. Buses are important, and there are also dust piles. So for example, this is Ahmed bin Ali Stadium. So we had two sensors, one here and one here. And across the highway, there are these large dust piles, which you can see from the Google Street View images that are still there. And so here I've simply plotted the as reported uncorrected sensor PM 2.5 versus sensor PM 10. And we find that at Ahmed bin Ali Stadium, which are the solid markers over here, there are a lot more times when the PM 10 is significantly higher than PM 2.5, which is an indicator of dust influence. And that is when wind is from this dust pile, it's affecting the stadium. And so we are working with FIFA to try and mitigate this source of hyperlocal air pollution, as well as trying to control pollution from the diesel generators. And so this is how low-cost sensors can play a vital role in air pollution mitigation, even in a well-monitored city like Doha. I will summarize the work so far, because we have been looking at air quality in well-monitored cities in Pittsburgh and in Doha. And generally speaking, we need to look at, oftentimes you look at low-cost sensors. People often report an R squared, but that's not sufficient. You also need to know accuracy and precision error, especially to track hyperlocal differences. Machine learning algorithms are really important for getting good quality data from nitrogen dioxide and ozone sensors. But all our algorithms are openly shared, but a lot of manufacturers do not necessarily share their algorithms, which I believe is needed to build trust, public trust, especially in the use of sensors. But also what you found, and this I did not talk about, is that the machine learning algorithms can hide sensor degradation, as you found with NO2 sensors. This was work conducted by postdoc J.O. Lee, who's now a faculty member at the University of Miami. And so we do need to look into the raw data as well and periodically collocate the sensors, especially NO2 sensors, with reference monitors to track their performance. And finally, PM sensors, that's what I talked about a lot. And basically where I'm going here is that nephelometric PM sensors are useful to detect combustion or submicron pollution, whereas optical particle sizers are better for supermicron dust, but we still need real world corrections to get good performance out of these sensors. And so shifting from well-monitored cities to other parts of the world where monitoring is not very prominent. So there are huge gaps as seen in these OpenAQ maps, especially for both for PM2.5, there's this huge data gap in many African countries and also for NO2. And what we find is that many of these areas, Northern Africa, Western Africa, Middle Africa, Eastern Africa, they are quite estimated to be quite polluted based on satellite estimates and the limited on-ground, on-the-site monitoring that's available, surface monitoring that's available. But they're also the most sparsely or unmonitored parts of the world, whereas Western Europe, the US, are all pretty well monitored and have relatively lower pollution. And so essentially you need to track pollution before you know how to manage it. And this is work by Susan Annenberg, which estimated based that some of the cities in Africa are incredibly well polluted, especially Lagos, for example, has a population of 10 million people. And PM2.5 is estimated to be around between 70 microgram per meter cube or so. And so we do need to do more monitoring in these places. And this is where hopefully low-cost sensors can play a key role. So this is work that we started in 2017. Carnegie Mellon has a campus in Rwanda called CMU Africa. And so we worked with students at the University of Rwanda as well. And so these are master's students at the University of Rwanda who use the data for their master's project. And my collaborators here were Jimmy Gasore, who is now an independent consultant in Rwanda, and Langley Dewitt, who is now the executive director of IGAC, and many of you may know. And so we deployed 2 monitors here about 5 kilometers apart. And what do we see? We had about 16 months of data, which was probably the first long-term air quality study in Kigali. We do see variability, seasonal patterns in the data. And so the dry season, obviously, we see higher pollution than in the wet season. So rainfall obviously plays a key role in removing some of the pollution. Now, whether it's from local sources or transported pollution, we need to look at that. But trying to average that data across 5 seasons, for example, this is a typical day, average day in each season. This is the seasonal average PM2.5 versus time of day. And the green areas are during the wet season, and the blue shaded regions and the blue lines are from the dry seasons. And we see that there's significantly higher pollution in the dry season, probably because of transported forest fire emissions. We also see a sharp diurnal pattern. We see increases in the morning rush hour and in the evening as well. We also had a black carbon monitor next to the University of Rwanda site. And we find that based on the wavelength dependence of particulate light absorption, the morning peak is from vehicular traffic, evening peak is from vehicles and domestic cooking. And so, so this is data that we're able to get from low-cost sensors deployed over a long period of time. a rough estimate suggests that about half the PM2.5 in the wet season comes from local sources like traffic and cooking, whereas about 75% of the PM2.5 in the dry season comes from transported pollution. So this has implications for how Kigali or a city like Kigali can manage their local air pollution, but they would still be impacted by transported sources. And so maybe a regional framework is required to manage air quality region-wide. Kigali also has car-free policies on certain Sundays, and we find that that also is an indication of lowering air pollution on those days. So that may be one way, for example, low emission zones where traffic is diverted away from particular areas at particular times. That may be one way to manage people's exposure. Again, this needs further study, but again, this shows the potential of using low-cost sensors in a place where there isn't much monitoring. So based on that effort, we have then expanded that with funding from the French National Research Agency, or ANR, as part of the Make Our Planet Great Again program, as well as funding for Professor Dan Westerveld at Columbia University. So we have deployed sensors in Abidjan, Accra, South Africa, Kenya, and Uganda. And this is Professor Veronique Boye at University Felix Houphouët-Boigny. This is Professor Alison Hughes and Mr. Emmanuel Apo of the Ghana EPA, and this is Dr. Julian Bahina, who has now gone back to the University Felix Houphouët-Boigny. He was a postdoc working with me. Ezekiel Bagru is now doing a PhD with my group in France. And so we have deployed networks in different cities. And you can visit us at africare.org or follow us on Twitter, which is where we really are, honestly. So some preliminary data from Abidjan and Accra. We have a sensor at the University Felix Houphouët-Boigny and at the Abidjan City Hall. And then the US Embassy also has a monitor there. And then working with Professor Kofi Amega, who has deployed monitors in Kwashimian, I think Trinity Church in Accra and the Atomic Interchange in Accra. What we generally find is that there can be some variability, intra-urban variability in PM2.5. This is still preliminary results, but we see PM2.5 City Hall and Abidjan Embassy about similar, about 20 microgram per meter cube, and the university is a little bit cleaner here, and there's again some variability in Accra, though the Dwar Zulu thing is an uncorrected plant tower PM per air sensors that may be lower than was seen here. But again, we are able to deploy these sensors and apply some corrections by collocation with reference monitors and see intra-urban gradients in air pollution with the use of low-cost sensor networks. So we have deployed monitors as well in East Africa, in Nairobi. So urban background sites, Westlands at the UNEP office, urban roadside sites at two universities, Kenyatta University and University of Nairobi, and residential sites as well. And a lot of this work was, these sites were deployed by Ezekiel Waiguru, who was at that point a master's student with Professor Michael Guattari. And this has been his analysis, where he's looking at seasonality in PM2.5. And we find that the higher concentrations were again observed during the dry months of May through October over here, which is similar to what you're seeing in Rwanda. And the roadside sites were also seeing higher pollution than the other sites. Again, we see significant differences across the city, where we see the morning and evening peaks, rush hour peaks, again, closely related to traffic. But we see that the pollution can vary significantly from 20 microgram per meter cube to 40 microgram per meter cube of morning peaks at different sites across Nairobi. And so there are very few monitors in Nairobi till recently. So now there are 3 reference grade monitors. I think they're probably close to each other, including one that was purchased by the MOPCA grant and donated to the UNEP. And but we also need a higher density of monitoring in Nairobi to capture these spatial patterns. And this is where low-cost sensors, again, are proving to be really useful. And so the next step is to actually do some air quality modeling and try to figure out solutions and understand the pollution problem better. And so Waiguru is working on doing Shumir air quality modeling, advised by my colleague, Dr. Matthias Beekman. who's the director of OSU-FLU. And so these are preliminary shimmer air quality modeling results. And we find that, of course, there are these urban hotspots in Kigali, Kampala, and Nairobi, but also this huge, probably forest fires in Central Africa. In any case, when we compare the shimmer estimates for PM2.5 with the Kampala Embassy BAM, for example, shimmer seems to underpredict the observations in Kampala, but in Nairobi, it's closer to the observation. So again, we need to figure out why we are missing some of these pollution sources in the city, which may be due to issues with the emission inventory of the model. And so we are hoping to combine the sensor data and the model to improve emission inventories, and that's the focus of Igero's PhD thesis. We can also combine sensor data with satellite data. Again, satellites provide, one time a day window, for example, which might miss the peaks, pollution peaks, and this is where the sensors can provide diurnal variability in pollution, whereas satellites provide spatial variability that cannot be achieved by ground monitors. And so we are able to get better quality data combining satellites. The purple bars are the correlation, the mean absolute error, and the bias, by combining satellites and one ground sensor to evaluate the pollution at another site in Kigali, for example. Whereas the green bars are as if we had just one site in a city and you use that as a representative of the entire city. Obviously, we get much better performance with the combined satellite AOD and low-cost sensor data. So this is another way to use sensor data. Here, we are using ground monitors as a reference monitor in Accra, where we deployed it at the University of Ghana. And the first 2 weeks of data here, the y-axis is the TROPOME estimate of surface NO2, and or rather the column density. And then this is the University of Ghana site where we deployed a reference NO2 monitor. So at least it seems correlated. So this is heartening. But over a year of data, the correlations are much worse. And so this is work that we need to understand why. And so we need to have these surface ground truthing of even TROPOME data with our ground monitors, and that's work that's ongoing right now. We do find that localized calibrations are really important. And so unfortunately, a lot of places in Africa do not have reference monitors. And so one of our efforts at AfriCare is we got about 25 TOM PM2.5 monitors that is facilitated a donation from the UK Environment Agency, facilitated by Christine Braban of the UK CEH, who are the host, I think, for today's talk. And so we have deployed about 15 of them in Kigali and 10 of them in Ghana. Several have already been deployed and working. The hope is that they are providing local data as well as providing calibration points for low-cost sensors, and they can also be used for training of the local STEM workforce, which we're already working on with colleagues in Ghana and Kigali. But of course, this requires additional funding for in-country partners in installation and operation. So to summarize, so hybrid air quality networks obviously reveal spatiotemporal variability in cities across Africa, but they need to be corrected by collocation with reference monitors. They can also be used to qualitatively identify local and regional trend sources, as well as track trends in air pollution. But we still need traditional approaches with long-term monitoring and field campaigns. We also need source apportionment data, for example, chemical composition data. We need to improve our air quality models. And we need to invest in key infrastructure, and we need to support local scientists. And that is the work that still needs to be done. A lot of this work would not have been possible with the support of local scientists, who are not very well supported, unfortunately. And we're working on that, but we definitely appreciate more support for their efforts, because they, at the end of the day, they know what their country needs. And so, and this I didn't talk about, but air pollution will be bad or worse in unelectrified rural areas, and this, a lot of it is because of the way people cook, for example. So something to think about. And with that, I'll be happy to take any questions. Thank you for your attention.
Thank you very much, Dr. Subbu. So Thank you very much for the very interesting talk about wide monitoring network all over the world. It was really an interesting talk and exciting to see how you compared the model measurements with the model, especially with Shimmer, and found out the problems in the data. Because I noticed that disagreement in Shimmer for Kigali over in the beginning and at the end of the period in July.
Yeah.
So you explained that it could be due to the emission inventories went into the model at that period, which is yeah. Because when I saw the graph, I was about to ask, but you already explained it. Thank you very much. It was a really interesting and exciting talk. So we have a few interesting questions here, so I can read it for you. Yeah. So the first question is from Nivedita Chaudhary. She's asking, for calibration of air quality sensors, what would be the reference monitor? And if reference monitor is not available, how to effectively monitor pollutants?
Yeah, that's a good question. So the reference monitors are typically, EPA grade, EPA certified or TUV certified or other central agency certifying that this monitor is good for use in this country. So these are typically like a chemiluminescence monitor for NOx, beta attenuation monitor, or an aerosol spectrometer like the FIDAS for PM, or ideally, of course, you can have gravimetric methods for PM 2.5 and PM 10, basically filter-based collection methods, for example. If these methods are not available, there are some efforts to build at least national calibration models. So, for example, in the US, Caroline Bark-John of the US EPA has looked at collocations across the US of different purple airs and developed an average correction factor for the purple airs. I think similar work needs to be done in other countries. One of the efforts that we are hoping to do is actually establish a testing center in Ghana, for example, that will be relevant for West Africa. And so we will be able to develop, collocate different sensors with reference monitors and develop regional specific corrections, because corrections that are developed in the US, will not be applicable to conditions in Ghana or Rwanda, because the aerosol mix is different and the environmental conditions are different. And there are, for example, the Harmattan winds, which significantly shift the size distribution of aerosols, so their correction factors will be very different, for example. And so, but these efforts need to be made. There is a large sensor testing facility established by Professor Stuart Pickett at Northwestern University in South Africa. So that's providing some data as well. That's work being done by Brigitte Language. Yeah, more work needs to be done. I think there are efforts ongoing in India by Professor Sagnik Dey to do some evaluations of sensors at different cities. But yeah, I think more of these collocations need to be done. You can always try to do some hygroscopicity corrections, because that is a known artifact, but you're still not able to correct for changes in size distribution, for example, of PM sensors, which is pretty important. So that is something to watch out for.
Thank you. Next question is from Saurabh Sonwani. He's saying, thanks for the great talk. I wish to know the reason why the NEF PM 2.5 sensors reporting relatively higher values as compared to already reported values. That's another question. If I wish to check any PM monitor sensor accuracy, what are the things that I should keep in mind?
Okay. I didn't quite understand the first part. Can you repeat that?
Yeah, so the reason why the NEF PM 2.5 sensors reporting relatively higher values as compared to already reported values.
Okay, I think the NEF PM, so if I understand that correctly, I think, so nephelometric PM sensors are really looking at light scattering by particles. And at higher relative humidity, depending on the particle composition, for example, if there is some sulfate or hygroscopic organic aerosol in the mix, then that will take up water and the aerosols will grow in size. And the nephelometer basically looks at the scattering of the particle itself. It's not looking at the size of the particle. Actual, the PM standards, for example, are based for dry aerosols. So either you can dry the incoming stream of aerosols and remove any water taken up by the aerosol, or you need to correct for the hygroscopic growth of the aerosol before comparing it to reference monitors. So that's why it'll end up reporting higher than reference monitors. The second one is if you are trying to evaluate sensor performance. One example is AQ-SPEC. The South Coast Air Quality Management District has been testing a lot of different sensors for a few years, and they report their data publicly, and you can look at that. Of course, this is for testing in Southern California, which is probably nice weather all year round and very different pollution mix than other parts of the world, but at least it provides a sense of sensor precision, number one. So if you're simply trying to use a low-cost sensor network, if you're trying to deploy 10 or 20 low-cost sensors in a city, you're just trying to look at intra-urban variability in pollution. You want to make sure that they are all precise with the R-square of greater than 0.8 at least, so that both collocate all the sensors. If they are all precise, then at least when you deploy them across a city, you know that differences in measurements are due to actual pollution rather than sensor imprecision. That's number one. Number two would be looking at uncertainties. So ideally, you would collocate one of these with a reference grade monitor, and that will tell you plus or minus 4 microgram per meter cube, for example, is the uncertainty on a 1 hour average basis. So if you are seeing differences of say less than 4 microgram per meter cube between two locations, that might be due to sensor uncertainty and not due to real, real differences in air pollution. So those are the two things that I would definitely look out for.
Thank you, Ramesh. It's a question from Bhumidi Lakshmi Madhavan. She's asking, can we access this presentation after talk? There are several interesting results for reference. Of course, I'll send you the link. So that's me who had to answer.
Okay.
So she has another question. How is the US Embassy PM 2.5 measurements obtained?
Okay, so the US Embassy, so what the US State Department has done is they have deployed reference grade monitors at a lot of their embassies worldwide. So they are beta attenuation monitors, or more recently they've been putting up, I think, Teledyne T640s, which are basically like the FIDAS instruments. And these data are openly available on the AirNow International website or through OpenAQ.
So she has that associated question, which you partly answered, because her question is PM sensors are used, what PM sensors are used at the embassy? Is there any reference for the measurement technique, calibration, quality control, etc.?
Yeah, so that's all taken care of by the US Embassy themselves. So this is part of the program to protect the health of American employees who are working at these embassies. And so they have contracts with, what do you call it, with a company that comes in and does the required maintenance periodically. So that's all taken care of, and it's a reference grade monitor operated just like a US EPA monitor anywhere, in the US.
Okay, so another question from her. She was really listening to your talk, right? So, yeah, so it's another one. Did you try comparing the MERA2 reanalysis based PM concentrations with real-time PM sensor-based observations? I saw many papers where people are using the MERA2 reanalysis based PM concentrations. How reliable are these?
Yeah, wait for my next paper. No, this is actually something that we're working on. And what we're finding is that, so the MERA2 has been evaluated in the US, right? And I think the performance is pretty decent because the emission inventories are very well characterized and they have corrected for biases and things like that. We have compared them with our measurements in different African countries, looking at measurements in Kenya and Ghana and in South Africa, and we are finding that they are significantly wanting. The PM2.5, again, Meratu, basically is a reanalysis data set that combines GeoSChem, I think GeoS5, and then AOD, and there is some normalization done and corrections as much as possible. And it's a wonderful effort by colleagues at NASA. Well, I think, but there is, obviously lack of validation in many African countries where on-the-ground conditions may be very different. And so, much work needs to be done to improve data quality there, at least retrievals. But there's still some useful information to be gained from Meratu, and that's hopefully will be in our next paper soon.
That's great. Yeah, thank you very much. Another question from her. Are your PM sensors based on optical technique?
Yeah. Yes.
Yeah, so that was easy. And then the next one is, what is the best local sensors that we can consider for spatial network?
Yeah. So I think all low-cost PM sensors are optical sensors. It basically depends on whether they are using essentially like an nephelometric PM sensor, or which is typically the plant towers that you see in the purple layers, or the clarity nodes. And these are typically like $10 or $12. And the plant tower sensors are really nice. They're usually pretty precise. What we have found is that we still need to do an initial collocation of the sensors when we get this is what I think I mentioned earlier, is that you get like 10 or 20 sensors, you end up collocating them, and then you end up finding that a few of them are still bad. So you need to replace those, but the rest of them have an R-square of better than 0.8, plus or minus 2 microgram per meter cube usually, and the reported PM2.5, which still needs to be corrected, but they're pretty good in that sense. And so any sensor, well, as long as it is in a reasonably well-designed housing, a plant tower-based or a Sensorion-based sensor will work quite nicely. But again, that's only for, say, submicron PM, like combustion aerosol. For bigger aerosol, if there is a lot of dust or desert dust or construction dust, then you really need optical particle counters like an alpha sensor PC, and those things are typically around $400 each, and then you need integration and things like that.
Okay, thank you. So there's a comment from Sebastian Dietz. It's like, thank Subbu, great talk.
Okay.
And there are, I don't see any other questions here.
Okay.
So no more questions, but I'm just out of curiosity, I just want to ask you, because you have shown this pollution increased PM measurements in different parts of Africa and also in Qatar, and especially like Nairobi, Kampala and all. So there could be, when it comes to Africa, especially in Nairobi, when I consider the city size, it can be already larger than the country, Qatar. and there can be a lot of influence from sea salt in Qatar, while in Nairobi we don't have that. Where we're thinking about any kind of, so it will be totally different approach into these stations when we think about mitigation scenarios or anything. So were you considering about anything like that?
Could you rephrase it?
It's about apart from proper scientific research, where we're also considering about proposing any mitigation scenarios.
So that'll hopefully be the work of Waiguru's PhD thesis. So Waiguru is a student from Kenya, and he got his master's at the University of Nairobi, and now he's doing his PhD in France as part of my project. But essentially, our goal is that we are training local scientists to work, local early career researchers to work on air pollution problems in their country or region. You're right. I mean, I think in Qatar, there is a lot of desert dust influence or some sea salt influence. But there is also a lot of anthropogenic pollution as well in Qatar. So for example, we have seen those dust piles, which are obviously construction, like anthropogenic. There is diesel generators, which are local sources of pollution. So those are more readily identifiable. In places like Nairobi, there are probably more pollution from older vehicles, for example, or from cooking, like charcoal or biofuels, for example, in poorer, lower income neighborhoods. I think there was some recent work, mapping, mobile mapping of pollution using uncorrected sensor data from Priyanka D'Souza and others that showed some significant geographical variability potentially across Nairobi. And so, trying to correlate that with low income versus upper income neighborhoods, that would be something to look at. Uh, Something that I think Rwanda has done recently. So in a lot of these countries, the number one, the vehicle fleet is old, right? 10, 20 years old, usually. And number two, there are a lot of two-wheeler traffic. And so you also have a lot of, basically two-stroke engines and old, leaky, engine, motorcycles and scooters, essentially mopeds. So what Rwanda has done is they have started electrifying. I don't know what happened here. My video seems to be disappearing from time to time. Rwanda has started electrifying all their two-wheeler taxis. So they're replacing all their two-stroke two-wheelers, or generally two-wheeler petrol-driven two-wheelers with electric two-wheelers. So that's one way to reduce hyperlocal, or urban air pollution. The other way is to look at more electrification of buses, for example, or trying to, I think they're also trying to put in uh, different, so in Qatar, obviously, we're importing new vehicles all the time, right? And so they're much cleaner than older vehicles, which are often exported to countries like Rwanda or Kenya. And so what the government is doing there is actually imposing duties based on age of the imported vehicle. So older vehicles may be cheaper, but the duties are higher, so the savings are not as much. So you are more encouraged to buy newer, less polluting vehicles. And so I think those are the sort of things that we need to look at. Plus, these are developing economies, and really you need to move people away as much as possible away from polluting sources like biofuels or charcoal, trying to get them towards even LPG or LNG or more electrification. And of course, there's other development activities that usually end up traditionally in the US and Europe and other places. Development has been associated with increased carbon footprint and increased air pollution. But hopefully, many of these emerging economies in the global south are able to, learn and avoid the mistakes of the global north and, move towards cleaner sources of energy consumption that will help them develop their economy. But again, this has to come from local scientists who are working in these countries. I mean, as an American scientist, I'm not in a position to tell them, you need to do that. That's very helicopter science, and that's not something that we want.
Yeah, I can understand that. Yeah. So, yeah, thank you very much. That was really great. So I'll just, since I don't see any more questions, I'll hand over it to Pallavi to conclude for the concluding remarks.
Samina, there is one question by Sebastian.
Okay.
Yeah, he has just posted.
Okay, I didn't notice that. Okay. Yeah, okay, Sebastian. Sorry, Sebastian. So I wanted to ask, what do you think where the hardware is going? Is there a near future there, or is there any progress? What is it? Where is it going?
Oh, hardware, like sensor hardware, where it is going. I think, sorry, I'm just trying to get back to my first page here, which hopefully has my email. Yeah, so that's my email. So please feel free to send me an email at either of these email addresses. Sensor hardware, I think currently where we are is that we have pretty robust sensors for carbon monoxide and ozone. We don't have good sensors for NO2, at least at the levels that are commonly observed. Our PM sensors are, I think the combination of the Nephelometric PM sensor with the optical particle counter is definitely improving our ability to measure PM 2.5 and PM 10 and PM 1 even. But they're still optical counters with their, with the assumptions that you need to make about density and chemical composition. There have been efforts to try and do some gravimetric sort of, quartz crystal microbalance that's been going on for 20 years, and maybe someday it'll work. Yeah, I mean, I unfortunately haven't seen a lot of significant improvements in terms of PM measurements in the last several years. The optical particle counters and nephelometers are about as good as we are apparently getting. There has been some news about better NO2 sensors, but again, these are very early stages, and we haven't seen any actual, proof of concept at least deployed in at least one city. I think that's still, unfortunately, I mean, I'm not seeing a lot of activity there, and maybe that's where some effort needs to be made. People are definitely looking at more specific pollutants, like, for example, looking at acetone or specific VOCs. It's methane monitoring that needs to be done for sure. Currently, methane monitoring and VOC monitoring, like benzene, is of critical importance, especially given the amount of natural gas and petrochemical processing that happens. But unfortunately, the PIDs that we have seen are not very specific. And if you want to get into specific conditions, then it becomes really expensive. I mean, but the PIDs have been relatively recent, so maybe there's more hope there, and they can be better used and made cheaper over time. But yeah, I mean, I think I wish I could have better news about what's new coming down the pipeline, but that is an area of active research, and I think definitely more fundamental research needs to be done and encouraged and funded for sure.
Great. Thank you very much. So now there are no more questions. So Pallavi, to you for the concluding remarks.
Thank you very much.